in air traffic control, optimization algorithms schedule flights, and you could schedule the flights to mitigate the propagation of delays or also to reduce CO2 emissions. Then in statistical inference, you might want to fit the parameters of a physical model, could be, for example, a climate model, to some observed data. And you could do that with the maximum likelihood method, for example, which leads to an optimization problem. And during my PhD, I encountered optimization in various robotics test beds, so in various dynamical systems. So the first one is a project that I did with a student. So what we try to do is to push the envelope of what's doable with quad rotors. And so this quad balances an inverted pendulum system. And we used optimization-based techniques to perform this maneuver. So this flip, did you see the video, or was it shaky?
Yeah, we can see it.
You could see it, okay. Yeah. So that's one application where optimization was crucial. I also designed this flying vehicle. So this flying vehicle has 3 electric ducted fans, and it's pretty heavy. So it weighs about 8 kilograms, and it uses thrust vectoring for controlling the attitude. And the thrust vectoring is very limited because there's these control flaps here, but these can only be moved a certain amount. So so the system is unstable and non-minimum phase, and as a result, due to these input limitations, it's a challenging control system. And we used optimization-based techniques, essentially some model predictive control or approximations of the constrained LQR problem to find efficient control algorithms. And then the last application I want to share with you is this robot here. So we called it the Cubely. So it has 3 reaction wheels. So these reaction wheels, one is here, and these 3 reaction wheels are mounted orthogonally. And attached to each reaction wheel, there's a mechanical braking system. And so what we can do with this cube, we can balance on the edge and corner, but we can use the braking system to jump up. So as you see here in this video. And the challenge is that when you speed up the wheels and you apply the brakes, after releasing the brake, you would like to end up in the upright equilibrium, and the margin of error is roughly a cone of 1 degree if you speak about angles. So you have to be very precise, and so an important question is how to choose the initial wheel speeds so that after braking you end up near this equilibrium position. And we used essentially a learning-based approach. So the system would iteratively find the right initial wheel speeds. And this learning-based approach is essentially a Newton-based method. And so it has its root again in optimization. So in all these cases, we saw that optimization can be used to solve very complex tasks. And these were all very successful examples. So where are the challenges? And I think one of the main challenges is how can we create algorithms that scale to very large dimensions? And from a mathematical perspective, one thing which makes the analysis of optimization algorithms interesting is that an optimization algorithm should always perform well for a whole class of functions. It should not only work for a single function, but for a whole class. So there's an inherent robustness question associated with the analysis or the design of an optimization algorithm. Okay, and so if you have questions, just feel free to interrupt me and let me know. Yeah. So what I would like to discuss with you is essentially what people call the phenomenon of acceleration. And I think it's best illustrated in an empirical or numerical example. So on the left, I randomly generated a quadratic program, and I applied one version of an accelerated gradient method and the gradient method. And as you can see, the accelerated method beats the gradient method by one order of magnitude in terms of iteration, numbers of iterations. And the important thing to notice is that the complexity per iteration is the same or is roughly the same for both algorithms. And so this corresponds to an immense speed up. Right? And while this is known for a while, the precise analysis and explaining why this actually occurs and generalizing that beyond the convex setting, that remains very difficult. And this is what I would like to discuss with you in the following 20 minutes. And in order to do that, I would like to introduce some mathematical notation. So I'm interested in minimizing this function f. So finding x star, the minimizer of the function f. And in order to fix the ideas, I think it's useful to start with the case where f is smooth and strongly convex, which means that it has a Lipschitz continuous gradient and that it satisfies this bound here. Right. And so there's two constants in this bound. There's L, which is the Lipschitz constant of the gradient, and there's kappa. And kappa is called the condition number. And what's the intuition behind kappa? So that will be very important for the following. So if kappa is close to 1, this means that the function f has round level sets. So these level sets are symmetric and look the same along all dimensions. But if kappa is increased, so if kappa is large, then the level sets of the function f can become distorted. So they can be like elongated ellipsoids. So that's important to have this picture in mind. And we'll see that all the results that I will present essentially extends to the non-convex case. So with the notation in place, I can now state both algorithms. So here's gradient descent, just performing a step along the negative gradient. And here's accelerated gradient descent, where I used a version that was suggested by Professor Nesterov, so a constant step size version. And note that it has some interesting features. So first, you evaluate the gradient here at this position here, which is not exactly at qk, but at something which is shifted. And then it has these two constants, so the constant d here and the constant beta, and these are chosen as a function of the condition number kappa. Yeah, and we know from a theoretical analysis in the convex case that this accelerated gradient descent converges, so the function value converges linearly, where the convergence rate scales with 1 over square root of kappa. And this is in sharp contrast to gradient descent, which also converges linearly, but where the convergence rate scales with 1 over kappa, right? And so if kappa is large, the difference between the scaling with 1 over kappa and 1 over square root of kappa becomes very important. And this is, in fact, what explains here the performance gain on the left. It's a difference between the scaling with kappa. And so the question I would like to answer in the following is, can we find conditions that ensure that an algorithm converge linearly with such a rate, so where the rate scales with the square root of kappa as opposed to 1 over kappa? And this is what's called acceleration. So the scaling of the convergence rate with the square root of kappa. Okay, and to emphasize that this is a challenging question, here's a quote from Arkady Nemirovsky, a leader in the field, who says, "Let me add some words about the Nesterov method. As it is, it looks like an analytical trick. I would be happy to present you a geometrical explanation, but I don't know it." And so what I would like to do in the following, I would like to present you first some interpretation of this method, explain, essentially come up with a physical model that explains why this algorithm is something useful or so providing intuition for why this algorithm works well. And then in the second step, I would like to characterize more broadly the mechanism that leads to this fast convergence. And so I would like to analyze the role of these constants, d and beta, and also answer the question or ask the question, is this evaluation of the gradient at this shifted position really needed? Because that seems to be a key feature of this method. Okay, so if there's no questions, let's start. And so I would like to start with providing you an interpretation. And so it turns out that you can take this ordinary differential equation and you can discretize it with the semi-implicit Euler scheme, and I'll come to that later. And you obtain exactly the original scheme, the original discrete optimization scheme, if you insert a time step of 1. So with a time step of 1, you obtain the original scheme. And so what I will do is I will analyze both the differential equation as well as the discretization. And because by training, I'm a mechanical engineer, I would like to start with the differential equation. And so the differential equation, you can bring that in first order form. So you can introduce Q, the position, and then P, the momentum, and the rate of change of the momentum can then be expressed here by two terms. And one, you can interpret this term essentially as a spring force. So where the objective function f corresponds to spring potential. And the second part here is the damping. So these are the damping forces. And so the parameters d and beta, so the damping forces are given here. And the parameters d and beta essentially parameterize this damping. And now the question is, can we make sense of this of these damping forces? And what you can do is you can split up the damping into two parts. One is just a constant times the velocity, so a constant times the momentum. And I call that isotropic damping because it's the same across all dimensions. It's the same constant that is applied across all dimensions. And the second part here is essentially here, so that's the Hessian. So that's the second derivative of f. So I write delta here for that. So that's a local average over the Hessian of the function f. So that's essentially the local curvature. And so if the function is locally flat, then the damping is reduced. If it's steep, then this term will kind of increase. And it's also interesting to note how the velocity p factors in. So if p is large, then the interval over which this average is taken is larger than if p is small. And these two damping terms are balanced by the constants d and beta. And so let's remember how these were chosen in this Nesterov algorithm. So if kappa is close to 1, so we have a very well-conditioned problem, then 2d is close to 1, and so the emphasis lies on this isotropic damping term, which makes a lot of sense, because if we have kappa close to 1, we have level sets of the function f which are very round, and so there's no need of introducing a damping term that varies with the local curvature. But as kappa increases, this term here goes to 0, and this term here goes to 1. And so what will remain, so for kappa very large, essentially this term here dominates. And again, this can be reconciled with our intuition, because if the function is ill-conditioned, if we have ellipsoids that are very distorted, if you have level sets of the function f that are like elongated ellipsoids, then it makes sense to have this curvature-dependent damping term to adjust the damping according to the local curvature. Yeah, and as you probably imagine, in continuous time, so it's very straightforward to discuss stability. So to discuss whether this differential equation has stable equilibria, and it turns out that indeed local minima correspond to asymptotically stable equilibria of the differential equation. that I showed you in the previous slides. And how can you do that? Well, you can simply look at the energy and ensure that the energy function decays. Now, if the function is non-convex, then you need to bound this term here. But if you have, for example, upper and lower bounds on the Hessian, then this is not an issue. Yeah. Okay, so that's essentially the first interpretation and analysis of this continuous time model. Now let's look at the discretization. So as I explained, if you start with the differential equation and you apply the semi-implicit Euler discretization with a time step of 1, you obtain the original scheme. And now, how does this discretization work? Well, what you're doing here is essentially a simple Euler update on the momentum coordinate, and then you're using the newly computed momentum for the position update. And this will be very important. And so what's essentially behind this scheme? Well, you can divide it into two parts, which are applied consecutively. So if you apply these two parts in a consecutive order, you obtain the original scheme here. And the first part is essentially just an update with the non-potential forces. So with the damping forces. So what you could think of this as essentially dissipating energy. And the second part is a very well-known integration scheme called the symplectic Euler scheme. And this part is only dependent on the conservative part of the dynamics. So the Hamiltonian part of the dynamics. And so you could think of intuitively as this essentially as energy conservation. So what the scheme does, it alternates between dissipation, conservation, and conservation, etc. All right. And one very important thing to realize is that as kappa goes to infinity, we'll see that essentially this damping reduces. And so we're left here with the identity map. And at this point, we're left with a conservative dynamical system, so with a Hamiltonian system. And then you have to be very careful about the numerical discretization. Because it's easily, because if you just apply, say, the forward Euler, it's easy to accumulate energy over time, which would lead to instability. But the fact that this scheme here is symplectic means that essentially the Hamiltonian properties of this conservative part of the dynamics are translated to discrete time. And so this means that this integration works well, even if this part here, reduces to the identity. And we'll discuss that in further details in the following. Yeah. So that was the first part, essentially, of my talk, where I wanted to provide you with some intuition about essentially this physical model as a mass spring damper system that I believe characterizes quite well this optimization routine. Now, in the second step, I would like to characterize more broadly the convergence rate. So I would like to ask the question, well, how do these parameters D and beta affect the convergence rate? And what I would like to do, or let me know if you have questions.
Yeah, so I have a question on the previous slide. So when you're using symplectic Euler and the forward Euler together, so symplectic Euler preserves the numerical flow, but your forward or explicit or implicit Euler won't preserve the flow. So
exactly.
So applying them together, how would you guarantee that the flow will be the numerical flow will be preserved?
So it depends what you mean preserved, right? Because the dynamics as a whole, they're dissipative, right? So essentially what this discretization does, it splits the dissipative and the conservative part, right? And for the conservative part, you apply a symplectic scheme. So here the simplest, like the symplectic Euler scheme, because you want to preserve, as you say, kind of the Hamiltonian properties of only the conservative part. But now, yeah, but now you concatenate with the dissipative parts, right? Yeah, yeah. And it's true. It's then the question: what do you exactly preserve, or what kind of properties do you preserve in this combined mapping? And well, that's a very interesting question, and I can't answer that straight away. But at least if you just look at the conservative part of the dynamics here, you can say that the scheme is symplectic, and therefore you preserve the underlying Hamiltonian structure. Yeah, yeah. Okay. Yeah, yeah. So here, so I would like to discuss the convergence rate, and I would like to distinguish. What I would like to do is distinguish between stability analysis and rate analysis, because in optimization this is sometimes mixed up, and you typically try to do both at the same time. So what do I mean first with a stability analysis? So here's a very simple example. So we have this one-dimensional function which has two local minima, and I initialize now the continuous time algorithm or continuous time dynamics from different initial conditions. And as you can imagine, depending on where you start, you converge either to the first local minimum or the second local minimum. And so the stability question would be, or parts with the stability is essentially, can you determine the region of attraction of each of these local minima? And so here's a picture when we add some more trajectories. And the way to do that, or one way to get an idea of the region of attraction, is clearly to look at the energy function. Because in continuous time, we know that energy is dissipated along the trajectories. And so if we know that we start here in this valley where the energy is too low or low enough, then we know, because energy is dissipated, we're going to be trapped in this valley here. And so we're converging to this point here. And similarly, if we initialize our algorithm with a certain amount of energy that is low enough, we will be trapped in this region, and so we'll converge to this point. And essentially, the boundary of these values is given by the level set of the saddle point, right? So we can look at the energy level set at the saddle point, and this divides the state space into two parts. And we know that if we start from here, we'll converge to this equilibrium. If we start from here, we're going to converge here. So analyzing the energy function and analyzing the topology of the energy level sets essentially at least partially answers the question about stability and the region of attraction. So given that we have stability, given that we know that local minima correspond to asymptotically stable equilibria, and that we have a rough idea of the region of attraction, I would like to find the rate now. And so the aim of characterizing the convergence rate is to find a bound, essentially that characterizes the distance between your current iterates to the equilibrium, and upper bound that by a constant times the initial distance times something that decays with here a certain rate alpha. And what I will do in the following is I will concentrate on this rate alpha here, but I will neglect or I will not try to characterize the constant here. And so how does the picture look like intuitively? We can look here at this interval, say from 0 to 5, that's time on the x-axis, and then we can plot some trajectories. And so the aim is to find this bound. So we could now, just as an illustration, plug in c equals 2.5 and alpha equals 0.2, and at least for these five time units, it seems a reasonable bound. But the thing is that over this finite time interval, what we can always do is we can increase the constant c and increase alpha, and we obtain another seemingly valid bound. And so what that means is that essentially this constant alpha is only determined by the behavior of the trajectories for very large times. Because if we just consider a compact time interval, we could always scale C and scale alpha. But for very large time, essentially, because we know that trajectories are asymptotically stable, for very large time, we're going to be very close in the neighborhood of the local minimum. And so intuitively, so this is just the intuition behind the result that I will show you next. So intuitively, what we conclude is that the global shape of the function f determines the region of attractions and essentially the answers a stability question. But the local shape, it's the local shape that determines this constant alpha here. And the following, and so this intuition can be made precise with this proposition. So if we have dynamics that are smooth enough, and if we have an equilibrium which is asymptotically stable, which has a certain region of attraction, and if we have if we linearize the dynamics around this equilibrium and we come up with a certain bound, so we know that the linearized trajectories converge with this rate alpha, then what we can do is we can conclude that essentially for the full nonlinear dynamics, trajectories converge at the same rate, so the same rate alpha, but we need to plug in a modified constant C tilde. So we have essentially this bound that characterizes the convergence rate for all initial conditions in this compact set. And I mean, the proof is elementary and essentially hinges on the following ideas. So because the dynamics are smooth, you will have a continuous dependence of the trajectories on their initial conditions. And then in addition, the set A is compact. So we're restricting ourselves to a compact set in the region of attraction. And these two properties combined, these can be used to guarantee that there's a maximum time until trajectories starting from the set A will reach a neighborhood of the equilibrium. So we can conclude, using these two properties, we can conclude that there's a finite time after which trajectories starting from A will be in an epsilon neighborhood of this equilibrium. And once they're in an epsilon neighborhood of the equilibrium, then essentially the convergence is determined by the first order approximation, so essentially by the linearized dynamics. And I find this very neat because what we can do now, if knowing that we have asymptotically stable equilibria, we can characterize this rate alpha here simply by doing a linear analysis and essentially an eigenvalue analysis of the linearized dynamics. And this is what we're going to do in the next few slides. So in continuous time, we already discussed stability. So we can now determine this rate alpha simply by looking at the eigenvalues of the linearization. And when you do that, we obtain this expression here, where there's this constant h involved. And this constant h is essentially the Hessian of the objective function evaluated at the local minimum. And if we assume, for example, that the function is locally strongly convex, then we don't know precisely this h, but we know that h essentially varies between 1 over kappa and 1. So what we need to do is we need to determine the worst case, the worst case convergence rate, so the worst case real part of these eigenvalues. And we can distinguish several cases, so we can set beta equals 0 first, and then we can analyze how this damping parameter affects the eigenvalues. And what we see is that if we have small damping, then the eigenvalues will be complex conjugate. And as we increase h, they will move up and down. So up, one eigenvalue moves up, one eigenvalue moves down along the imaginary axis. And if we increase the damping, at some point they will become real, at which point the real part here decreases for low values of h. But what we can conclude, because we're only interested in the scaling of the worst real part of the eigenvalues as a function of kappa, what we conclude is that essentially this favorable scaling is only possible if this constant d scales with 1 over the square root of kappa. So if the damping is too small or the damping is too large, there's no acceleration. And similarly, if we look at the case where beta is not equal to 0, then, well, what this parameter beta does, it it essentially adds some negative real parts of these eigenvalues for larger values of h. But we can again conclude that if the damping is too little or the damping is too large, we don't have this favorable scaling of the convergence rate with kappa. And so this is kind of the result in continuous time. As long as these parameters d and beta scale with the square root of kappa, then we have accelerated convergence. Yeah. And now the interesting thing is that we can use essentially this mechanical or physical model that I showed you to apply essentially the same type of analysis in discrete time. So first, and we can again apply this proposition where we can, knowing that if we know that equilibria like local minima correspond to asymptotically stable equilibria, then we can characterize the rate by looking at an eigenvalue analysis of the linearization. And so for applying this proposition, we first need to discuss stability. And so let's discuss the stability question. And what we can do is we can take advantage of the fact that this discretization scheme can be divided into this dissipative step and this symplectic step. And here, because this scheme here is symplectic, what we can do is we can apply backwards error analysis, and we can find a perturbed energy function, which is almost exactly preserved over this part of the step. So remember, for the continuous time analysis, we answered or characterized the region of attraction by looking at the energy function. Here, because we do the symplectic discretization, we can find a perturbed energy function, and we can use this perturbed energy function for analyzing the region of attraction in discrete time. And here's, sorry, I'm having some issues with the presentation, but I hope it should work. Yeah, so here's the precise result for that characterizes this perturbed energy function, h tilde. So what you do is you do a truncated Taylor series expansion. And this is typically called backwards error analysis. And so we came up with the following bound. So this characterizes the change of this h tilde. So the change in energy for one of this symplectic step. So for one step of the symplectic, so only the symplectic Euler step. And this bound here essentially is something with e to the minus something divided by t. And so if t is small, so t say 0.001, then the bound we obtain here is extremely small, so 10 to the minus 33, which means that essentially this perturbed energy function is virtually exactly preserved over one step of the symplectic Euler scheme. And so in the following, I will just neglect this term and say it's exactly preserved. And more importantly, we were also able to come up with bounds that characterize the difference between the original energy function and its perturbed energy function. And you can use these bounds for stability analysis. And so essentially you can use this perturbed energy function to discuss stability in the same way as we use the original energy function for stability analysis in continuous time. Okay, and once we have stability, we can then argue about the convergence rate by looking at an eigenvalue analysis of the linearization. And the picture will be very similar, except that we're in discrete time, so we need to look at the absolute value of these eigenvalues. And we again ask the question, how do these eigenvalues change as we vary h between 1 over kappa and 1? And we can again distinguish the same cases. So if beta is equal to 0, then the eigenvalues here move along concentric circles. If the damping is small enough, and then if the damping is larger, then at some point they become real or move along the real axis here. But the conclusion is very similar than in continuous time. So as long as the damping parameter d scales with 1 over the square root of kappa, we have this favorable scaling of the convergence rate. And the same type of analysis applies in this case where beta is greater than 0. Yeah. And so this characterizes the set of parameters which leads to this accelerated convergence, meaning that you can essentially find a time step t which is independent of kappa, so that your trajectories converge linearly with a rate that scales with the square root of kappa. So you have acceleration. Yeah. And I think one very interesting corollary of this result is that you can actually set beta to 0 and d equals 1 over square root of kappa. And so you obtain this heavy ball scheme. And the previous analysis shows that as if t is small enough, this is accelerated. So your convergence rate will scale with the square root of kappa. And the bound that we obtain is 0.001. But this essentially shows that this, in principle, this shifted evaluation of the gradient here, which was one characteristic property of the Nesterov method, is actually not needed for if you just care about acceleration. Yeah. So if we go back to the quote from Arkady Nemirovsky, he asked for a geometrical explanation. What I provided essentially was a mechanical analogy or a physical analogy. And so I think from this perspective, what causes acceleration? Well, it's really the fact that we have a system with inertia. Because if a system has inertia, it tries to keep its velocity. And so it's robust. So the convergence rate will be robust against small changes of the spring. So yeah, and these changes in the spring correspond to changes in the curvature. And the previous analysis kind of made this observation rigorous. Yeah. And with that, I would like to conclude. I would like to thank my PhD advisor and my postdoc advisor for the support they gave me. And I would like to thank the Braunko Weiss Fellowship and the Minute program for the financial support, and all my colleagues at the ETH Zurich and UC Berkeley for the wonderful time we had. And finally, as you know, as was mentioned before, I was recently appointed independent group leader at the Max Planck Institute for Intelligent Systems. And so I'm very actively looking for PhD students who would be motivated and who would be interested to work with me essentially at the intersection between machine learning, control, and optimization. And so I would be open to do some theoretical research, but we could also use or evaluate our algorithms on the excellent test beds that we have here at the Max Planck. So here's a ping pong playing table tennis robot, and there's some manipulation robot, and the torso of a humanoid, for example, which we could use. Yeah. And with that, I would like to conclude, and I'm happy to take your questions. Yeah.
Thank you, Michael, for the great talk. And so, people, if you have any question, you can unmute yourself and ask him that directly. Okay, so I will ask a question that in the last theorem that you mentioned.
Sure.
So
yeah.
There was a condition of f being analytic. So why is it needed?
Exactly. Analyticity. So it's needed for doing these Taylor series expansions. So what you do is you do a truncated Taylor series expansion, and you essentially use Cauchy's integral theorem for bounding the derivatives. And so that essentially there you need analyticity there. Yeah. But one thing I would like to mention is that because we're working with compact sets, essentially you can approximate any continuous function arbitrarily well with a polynomial, essentially. Yeah.
Yeah. Those Weierstrass or Stone-Weierstrass theorem.
Yeah, exactly, and that's also what I essentially use. Yeah, exactly.
Yeah. Okay.
Yeah. But it's very common. So for computing this perturbed energy function, yeah, you do a truncated Taylor series and truncated Taylor series expansion, and you need to bound the higher order terms that you neglected, and you use that by assuming that your function is analytic. Yeah. Yeah. Very good question. Yeah.
Yeah. Thank you. And
yeah, and I'm sorry. I mean, I didn't go into details there, so you really have to read my paper if you want to know the exact details. Yeah, but it's relatively tedious manipulation also. Yeah.
Yeah. Sure. Okay, then if there's no more questions, then maybe we can call it a day. And thank you again for accepting the invitation for this talk. And in the future, we will also look forward for many other talks from you, maybe. Yeah.
Yeah. Well, if you yeah, for sure, I would be happy to present again. Sure. Yeah. Cool, and I think it's great. So it's great that you have this control seminar, and yeah.
Mm-hmm. Yeah. All right.
Yeah. So have a nice evening, guys.
Yeah. You too. Yeah.
And I mean, let's hope that we meet each other at the conference at some point. That would be
sure.
fun.
That would be great. Yeah. Okay.
Cool. Ciao, guys.
Yeah. Goodbye. Yeah. Sure.
How? Yeah.
You have to exit.